Okay. Yeah. So sorry. I forgot that I had said I would do this. All right.
Okay.
So, do you understand the idea of representability?
Not really, although I maybe now I have some clue. It's
So, so here's like one of the first places that this was noticed was that every group, um, yeah. I'm hesitating just a little bit because we need to be careful about presentate finite presentations. Certainly, every finite group can be presented as a group of uh, uh, of permutations. So if you present some group that has some underlying set, uh, and then you can find a group which acts in the same way as the group that you've presented, but that is done entirely in terms of permutations. Does that make sense? So if I have
so.
so I mean, obviously every permutation can be undone, right? Right. So every permutation has an inverse. So that gives us a little bit of confidence that I can make groups out of permutations.
Are you talking about all possible moves in the group in a sense as permutations?
Well, yeah, we're all the elements of the group can be represented as permutations.
Okay, okay.
Yeah. So and then to get additional, so the permutations may make some distinctions, and you have to erase those distinctions with some additional equations. But by and large, there's a representation theorem. It says, you don't have to think about groups abstractly. If you really need a concrete representation, you can think about them in terms of permutations. So that's one way to use this the Cayley representation theorem. So Yoneda can be viewed as a kind of generalization of that for category. Uh, so if you have a locally small category, C. So by locally small, it means that the Hom sets are sets and not proper classes. Does that make sense?
Yes, yes.
Okay. So so then each object of your category, let's call the category C, gives rise to a functor from C to set. Okay. And so it's Hom A blank. Okay. So if you take an object from C, call it X, and you plug it into the blank, then you're now going to get a set. You're going to get a set of morphisms. Does that make sense?
Yes, yes.
Okay. And then you can also you can precompose. So if you have some functor from X to Y, um, say F, some morphism from X to Y, say F, um, then if you compose on the left, um, to a morphism from so you can now get a morphism that's in A to X to a morphism that's in A to Y. That's what makes this functorial. Does that make sense?
I'm not completely sure if so.
So you'll send X to the set of morphisms HOM AX and sends a morphism from X to Y to the morphism F ring blank. And so if you handed a morphism from A to X, it'll become a morphism from A to Y. Right? Because it'll be F ring G. Okay. And so you can so this is the covariant version. There's also a contravariant version where you put the object on the other side. Okay. So for each object A of C, the natural transformation
Hey, Greg, you're not sharing screen.
I'm not. I'm just talking.
Okay.
All right. So for each object A of C, there's a natural transformation. Okay, here we go. So you fix a functor from C to set. All right. So you've got some F that takes C to set. All right. Then you can find a natural transformation from the HOM functor that we just described to F. Okay, so it's going to be HOM of HOM of A blank F. So this goes from if we call the functor that we just described H sup A or HA, then the elements of that HOM set are in one-to-one correspondence with the elements of F of A. Does that make sense?
I mean, I am.
So here we go. Let's let me. I don't know if I can do a screen share. Let me. Yeah, I don't think I can do a screen share here. So think about the. You have all the functors in that run between. Sorry. Think of all the natural transformations that run between functors from C to set, right? So we're bumping up a level, right? So you have your category C, you have set, and you have all of the functors that that run from C to set, right? And then you can think vertically all of the natural transformations that run between those kinds of functors. Right. So are you familiar with what natural transformations are?
Yeah, but I have some problems because I'm thinking this in terms of, you know, some concrete programming language where, for example, in Scala, there's kind of types, and then between
Yeah, you can think about it like that. That's not, it's not too terrible. I mean, basically,
Mhm.
you know, if you have a it's a family. A natural transformation can be thought of as a family of morphisms, right? So essentially, it's a way of beating a, you know, a functor, for one functor into the shape of another, right? It carries you from one functor to another. So let's say I have a functor f that runs from A to B. Okay, so I've got some category A and I've got a category B, and f runs from A to B, and I have another category, another functor that runs from A to B. And what I need is morphisms that are going to take me from so I'm running from so imagine you have a little rectangle, okay, and I've got A along the top and I've got B along the bottom. Okay, so I have some object, um, uh, say X, and I want to consider, um, 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 and I've got some object Y along at the bottom, and I've got some morphism F that runs from X to Y, right? And I want to look at F of F, right? And I want to look at G of F, right? Does that make sense? So
Yeah, yes.
so okay, so I need to be able to go from the F of A over to the G of A, and then down the G of F, to the you know, to the, from the left hand corner, left upper corner to the right bottom corner. And so I run along, I run along from F of A over to G of A, and then from G of A down G of F. Sorry, I said A. I meant to say X and Y. All right, so um, I have F of X, and then I run along, um, for this F of X object. I have some morphism that's going to take me over to G of X, and then I run down from G of X to you know, G of that morphism, which is F, to G of Y. And it's got to be the case that if I also run down F of little f, so I'm going from F of X down to F of Y, then I have to be able to run along along the bottom line of that diagram. So that's going to be G, so F of Y over to G of Y. So the natural transformation is this family of morphisms, the components, which are running, you know, F of X over to G of X, and F of Y over to G of Y. So those morphisms carry you from the F to the G, right? And then it has to be that if you go, which no matter which way you go around the rectangle, it's the same. Either path gives you the same results, right? Or in other words, the diagram commutes. So that's the idea of a natural transformation.
So, if I understood, you're saying that we can apply, first we can apply just the morphism of the elements from X to Y, and then the natural transformation from F to G is the same as going to F to G and then applying the morphism from the elements X to Y.
That's right.
Okay. Okay.
So the two components of the natural transformation in that diagram, there's a component that runs from, you know, big F, which is the functor F of X. So there's some natural transformation, call it N, and there's a component in sub F of X, which is going to run from, or in sub X. And what it does is it runs from F of X to G of X. and there's n sub y, which runs from f of y to g of y. And what we're saying is that that g of y ring n of x is the same as n of y ring g f of f. Does that make sense?
When you say ring, what do you mean?
Compose.
Oh, okay, okay.
Function
Okay.
composition.
Mm-hmm.
Okay, so once you have the natural transformation idea in your mind, and it's worthwhile to look at, like, so it's really not so easy to understand monads deeply unless you understand natural transformations, right? Because a monad is 3 data, the functor, and then 2 natural transformations. So you have some endo functor, which is running from C to C. So C is your category. Let's say T is your monad, and T runs from C to C, so it's an endo functor. And then the unit is a natural transformation from the identity over to the over to T of, over to T. So you have a natural transformation from identity to T, and you also have a natural transformation from T squared to T. Right? So monads entail natural transformations. But the other. Go ahead.
Sorry.
Go ahead.
So when you say endo functor, you mean natural transformation from in the same category from the same category to the same category.
An endo functor is a functor from the category to itself, and then the natural transformation is between these 2 different endo functors.
Oh,
right?
Between. Oh, I see.
So natural transformation is a way of converting one functor into another functor.
And in this case, this is the same functor because.
No. So in the case of a monad, you have 2 different natural transformations. One functor is the identity functor, and the other is the functor T. That's the unit one. And the other natural transformation is from T squared, so T applied to T, right, over to T.
Oh, I see.
Yeah.
Oh, I see. T squared is different
than T.
Than T. This is a different category. Oh. Okay.
No, it's the same category. It's still C. T goes from C to C. So T squared goes from TC to TC, right? But, if the image of T is all of C, which may or may not be the case, then, but certainly think about the identity goes from C to C, and T goes from C to C, right? Mm-hmm. So you have this natural transformation that goes from identity to T, and T squared goes from T of C to T of C, and which is properly inside C. So you could think about it as going from C to C, right? And then you have a natural transformation from T squared to T. That's the monad. More generally, in the same way that a category is built out of objects and morphisms, you can also build a category out of functors and natural transformations. Right? So it's one level up. Right? Functors go between categories, but we can build a category out of functors and natural transformations. Right? So it's one level up from before. right? So now in terms of the Yoneda lemma, so when I consider the Hom set of natural transformations between HA and F, right? Then the objects of that Hom set, right, are in one-to-one correspondence with the elements of F of A. So let's go over the data one more time. I've got F. It runs from C to set. Okay, now I can consider all the natural transformations between HA, which is our Hom gadget, and F. Okay?
Okay.
And it will turn out that those are in one-to-one correspondence with the elements of F of A.
And the elements of F of A are all the functors, or
No, F is a functor, right? It runs from C to set. So A is an object living in C. When I take F of A, I'm going to get a set. So for example, here's one. There's a category of groups and group homomorphisms. Okay. And now I'd like to go from that category to the category of sets and functions. Well, the forgetful functor will do that for me. So I just I forget all the group structure and just pick out the underlying elements of the group. Right. So that's a functor from the category of groups and group homomorphisms to the category of sets and functions. Does that make sense?
Yes.
Okay. So F is like one of those. So C is in that example, C is the category of groups and group homomorphisms, and the forgetful functor on that takes you from that category C over to set. Right. So if I pick out some group, call it A, and I apply F to it, then I've just forgotten all the structure on the group and just have the underlying set. Right. So F of A in that case is just a set. Now it turns out that set is in one-to-one correspondence with the natural transformations between H of A. So A is some group, right? And remember what H is. So H is going to take objects to Hom A blank, right? So it takes an object X to Hom AX, and it's going to take morphisms F to F ring G. So it precomposes F. That's the definition of the HA functor. So I have a functor F that's running from C to set, and I can consider all the natural transformations from HA to F, right? So it's a way of turning HA into F. right? So it's going to have a bunch of components that run from HA X over to FX and HAY over to FY, right? So when you go around the diagram, it's the same. So each one of those natural transformations is in one-to-one correspondence with the elements of f of a.
Can you say more about when you say home set and a comma blank?
Sure.
What this means?
All right. So the hom gadget in a category is all of the morphisms that run from. So when I have some, let's say I have some category C, and I have two objects in C, then I can ask for hom A B, right? So an object A, an object B, and I can ask for all of the morphisms that run from A to B in C. Does that make sense?
Yes.
Okay. So that's what hom, and so now I could not fill in one of those. I could say hom A blank, right?
And you're saying all, you mean all of the morphisms from A?
All of the morphisms from A to something. When you give me a something, then I get all of the morphisms from A to that thing. Let's call it X. Right? So that's the hom. So that when you're, that's why at the beginning we said that C was locally small, because that says what kind of gadget the hom calculation is. So it turns out that you can make the hom gadgets be very structured. So when we have an enriched category, the hom gadget can not just be a set. It could be a group, or it could be a quantile, or it could be a category. But in this case, when we say that the category C is locally small, then we're saying, hom AB is a set. And it's a proper set. It's not a class, right? So it doesn't, its cardinality is, like we don't run into things like set of all sets kind of stuff, right? So its cardinality is a proper set. Okay, so hom A blank, we're going to take, so the little HA is, we're going to describe a functor, and it's going to go from C to set. Okay, so that functor takes an object A over to hom A, sorry, so for each object A, we can describe a functor, right? So it takes hom A X. It takes X to hom A X, right? Does that make sense? Right. So
Yeah,
you
X
give,
is like a, oh yeah.
X is an object from category C. Right, and so our functor HA goes from hom A to gives you back the set hom AX.
I see. Can we say that X is, we are like creating a function, we're saying that X is a parameter to the function. Result
That's
is
correct.
hom.
That's right. Yeah, well, remember what a functor is, right? A functor has to take objects in your category C to objects in your target category. And it has to take morphisms in your category C to morphisms in your target category.
So we are creating a functor from elements in C, which is X, to a home set, which will be
to the category set.
To the category set, where
so if you have an object X in C, then the set you get back is all the morphisms from A. Sorry, if you have an object in C called X, then we're going to get a set that's all the morphisms from A to X.
And this is called home set, right?
That's the home set. Yeah, okay. Exactly.
Okay.
And
okay.
if you give me a morphism from X to Y in C, then the functor HA goes by precomposition. So then you have a if you give me a morphism G, then I'm gonna from Y to something else, then I will I'm sorry, from A to X, then I'll precompose it and I'll get a morphism F ring G that's in the HOM AY. Okay, so it's clear, and you should check functoriality, right? That it preserves identities and it preserves composition. It should be obvious that that's the case, but check it for yourself. Okay, so so for each object A, HA is a functor. Okay, HA is a functor running from C to set. Now, if I have a functor F that runs from C to set, then the elements of F of A are going to be in one-to-one correspondence with the natural transformations between HA and F.
I see.
Okay, that's the Yoneda lemma. It's giving you a representation theorem.
And we cannot do this for sum types, right? Only for product types to get representable.
We're not mentioning sum or product types, right?
I was listening to Bartosz to say that, so I'm wondering why is that the case?
So what you're asking about is the nature of F. So F might be a kind of type constructor. But here, if F is equal to the sum F1, F plus this joint union of F1 plus F2 plus F3, it still works. If F is equal to the product of F1, F2, F3, it still works, right? So I'd have to look more specifically at the point that he's trying to make. But the main thing is F is an arbitrary functor from C to set. Any old functor from C to set. Then we can always get a representation of the application of F to A. But it's kind of it's a really funny sort of thing, because in general, how do I say this? Category theory is always sneaking set into things somewhere, like really rooting out set as the notion of collection that's hanging out in the background is much more challenging than it appears. So in particular, calling Yoneda important means that you're you have oriented yourself or your thinking towards set as your notion of concrete representations. But, you know, from the point of view of type theory, or the point of view of computation, set is not necessarily your best representable. So it's a very, very stark slant towards set theory that is accidental, right? We could have developed mathematics without set theory. We could have started, Cantor could have discovered type theory instead of set theory, right? Or we could have had the lambda calculus before we had set theory. It's not necessarily the case that set theory is as foundational as its current place in mathematics. But that's just my own idiosyncratic view of things. Anyway, that's Yoneda. I'm sorry I didn't have any slides, but sometimes it's actually better if you visualize these things in your mind rather than having the pictures. If as we're talking, you construct the pictures in your mind, that extra little effort really helps a lot. At least that's been my experience.
Yeah. And I could make the image because I was looking at this Bartosz video, so I could represent this in my mind.
Sure. Yeah, it is tricky keeping all the levels in place. There's multiple levels, right? Because you've got your category, you've got your Hom set, and then you've got the natural transformations between the H, A, and F, right? So those are happening at different levels.
Yeah, I wanted to ask you, how can I think about? I mean, it's easy to say you have categories, and then you have some morphisms, and then you say, okay, now all the morphisms are the categories, and natural transformations are the elements, and natural transformations are the morphisms. And now I'm totally lost. I'm not sure how can I easily switch. I don't really know how to represent this, how to think about this when I switch levels.
When you climb levels, yeah, you just have to be careful, right? The thing that's valuable about category theory is you can just be abstract. You can say, all right, my category is made out of these objects and these morphisms. And so when you climb up a level where the objects are functors and the morphisms are natural transformations. And you can even go further up. You can say, well, the objects are natural transformations and the morphisms are what are called modifications. And in fact, there are these n categories, right, where you've got where it's not fixed. You've always got a next higher level, right? You've got infinity categories where, you've got 1 cells, 2 cells, 3 cells, 4 cells. So each level can be defined in terms of the level below it. Right. So objects are 0 cells, morphisms are 1 cells, and then morphisms between morphisms, right? There are 2 cells, and then morphisms between 2 cells or 3 cells, and so on and so forth.
And what this means, I mean, like computationally, what this means, creating this infinite categories. Are these like the dimensions, or is it going from one level to another? Is it like very computationally? We are expanding something. how to think about it?
Well, actually, that's a great question, right? There are many different definitions of in categories, and there's not agreement. There are, as far as I know, 6 different proposals for how to define in categories, and there is no agreement on which one is the whether or not one of them is more compelling than another.
I see. Because when you listen to someone explaining category theory, it's like, oh, this is like starting from very simple stuff, objects and morphism, and like that's it. But nothing interesting is between just objects and morphism in this way. The interesting stuff begins with when you have like more complicated categories, right? As you said, like
well, let's be careful, right? So like you can typically a lot of classical mathematics fits into that framework, right? So sets and functions, sets and relations, those are all just, plain vanilla categories, right? Already we've got sets and functions, right? So that's all of set theory. Sets and relations, right? So, relational algebra all falls into that. All of group theory, groups and group homomorphisms, all of topology, topological spaces, and homeomorphisms. The list goes on and on and on. So a lot of classical mathematics fits in that framework. Notice that computation does not fit in that framework. So here's what I mean. Okay, so in general, to talk about a computational system like the lambda calculus or the row calculus or the ambient calculus, yada yada yada, right? So what do you have to have in order to have all those? In order to have one of those kinds of things, so you need some generators. So that's going to be your grammar, right? And then you need some equations. That's going to be your structural equivalence, like alpha equivalence, or that the fact that par and 0 is a monoid, right? A commutative monoid. So you have generators, your grammar, your structural equivalence, and then you have some rewrite rules, right? So you have, in the case of lambda, you have beta reduction. In the case of rho, you have the com rule. You have a similar kind of set of rules in the ambient calculus. So you have three data, right? Grammar, your equations, and your rewrite rules. Okay, so now what structure do you preserve to build the category of those things? So it is not obvious at all, right? How I convert. In fact, it's an open question in terms of what kind of conversion there is between pi and ambient. So it is not clear how category theory applies to computation at that level, but that's the right level to talk about computation. So category theory is good for some things, but it's not really well suited to talk about computation. And this is largely to do with the fact that category theory is very functionally oriented, but computation is not necessarily about functions. processes are not functions. Some processes are functions, but most of them are not.
I see. So in this example, categories are like pi calculus is one category, lambda calculus is another category.
No. In the example I gave, no, they're not categories. In the same way that a group is not necessarily a category, or a topological space is not necessarily a category, right? So in the case of a topological space, we have topological spaces and homeomorphisms that forms a category, right? Does that make sense?
I'm not sure.
So, I mean, a topological space is just a set together with a subset of the power set that has certain properties. Like you've got all unions, and you've got finite intersections, and the set and the empty set are included. Right. Okay, that's a topological space, right? So, but that's not necessarily a category. Right? You have to work to think about that in terms of a category. All right. So, but if I have my objects are topological spaces, my morphisms are homeomorphisms. In other words, they preserve the topological structure. Right. So that's clearly a category. Now, what I described was the objects are going to be these notions of computation. So you've got your grammar, your structural equivalence, and your rewrites. That's your thing, right? Now, what are the morphisms between those things?
We don't have it, right?
Well, maybe there's one, but no one has put forward a convincing proposal. So we've had category theory for a long time, right? Like, 70 years, something like that. 1950s to now, 70 years. So we've had category theory for a while now, and we've had computation for a while, right? The 1930s. So 20 years more than so 90 years. We've had computation for 90 years. We've had category theory for 70 years. In that time, no one has put forward a convincing notion of a category of computational systems.
So you're saying that if we have something like lambda calculus and whatever rewrite rules we have, the morphisms between different states of execution.
No.
These morphisms, or
No. You've got your whole object is the lambda calculus. Another object is the pi calculus. The morphisms go from lambda to pi.
Oh, okay.
Now take a lambda term to a pi calculus term.
Oh, I see. Can we define something like that? Because
well, you know how to translate lambda into pi. That's clear.
Oh yeah. I see.
Translating pi into lambda is not clear.
And we don't. We don't have this.
You don't have par, right?
So we are now programming concurrent programs in lambda calculus, although we don't know how to implement this.
That's right. Similarly, another whole object in this would-be category, this thing that we would like it to be a category, would be the ambient calculus. And now we don't know how to go from ambient to pi that in a way that is, we don't know what structure we want to preserve.
So Greg, when you say computation is processes, are you saying that we cannot always decompose those processes into component sequences of functions? Is that what you were saying?
No, it's more like functions are very clear. You have some number of inputs and you have one output. That's what a function is, right? But processes don't work like that. So just ask yourself, what does high water mark compute? It's a protocol. It doesn't compute anything. It guarantees a property of a channel. Another question is, what does the internet compute? It doesn't, right? That's not how the internet works. That's not the way we think about the internet. It doesn't have an output.
I see.
So monad is just one thing that can like represent one aspect of this. But if we want to represent like par in lambda, this is like we don't have anything for that.
That's correct.
So
You can.
we are all now trying to do this, right? With different libraries and
That's correct. That's exactly right. And in fact, this is one of the things that really the import of what I do with my little table, where I talk about the 4 properties of computation: completeness, composition, concurrency, and complexity, right? What I'm really arguing for is that completeness is only one aspect of computational expressiveness. Compositionality is another aspect of expressiveness. Concurrency is another completely different aspect of expressiveness. Complexity is another completely different aspect of expressiveness. So when you look, reflection is another completely different aspect of expressiveness. Each of these different characteristics are aspects of expressiveness, and many people do not understand that completeness does not cover these other aspects of expressiveness. And
when you say completeness, what exactly you mean? Like totality or
like Turing complete or things like that. Is that what you mean?
Yeah, that's right. Can I represent all these computations this way? Right. So you could come, if you make certain assumptions, you could come up with a pi to lambda, right? So if you did coroutining, for example, but that makes some very specific assumptions about concurrency. As soon as you have true concurrency, then you're screwed, because pi is not confluent and lambda is. So you are literally screwed. There's no path from pi to lambda that is faithful, in the sense that you have you can represent non-confluence. In fact, I was having a conversation on Twitter on exactly this point, right? It's like people in functional programming are so happy about all these nice properties, and then you say, yeah, but that's not life, right? That you're living in a toy universe that's terrifically impoverished. Do you really want to use an airline traffic system that is confluent?
Yeah.
No, you really don't. Because it would, confluence for an airline traffic system would mean that either you have an infinite supply of seats on the airplane, so it's not going anywhere, or you have no seats on the airplane. And so it doesn't matter if it goes anywhere, you're not on it. Anyway, it's time for the dev stand-up. Thank you all for the time and attention, and we'll look forward to this Casper next week.
Thanks
All
for
right.
detail.
Thank you.
Thank you.
Thank you.